So good morning. Welcome to Krishna's class. Last time we have touched the nature of discontinuities of a of- in this talk we do a structural theorem for subsets of R with the outer measure finite. This is what is called Vitali's covering. The result is very much and it's a comparison to one is one. Okay, so let us start definition of what is a Vitali star. So what we try to do is the following. Try to cover or establish that there exists a set of intervals which are called the Vitali cover, and a finite number of such intervals you can almost cover the set with measure finite. So let us start defining the Vitali discovery. Sorry for that mild slight interruption. Okay, right. So let me define what is the Vitali discovery. Let P be a subset of R with and let G be a collection of intervals of positive. We say that G is a Vitali cover of E if for every epsilon positive there exists and x belonging to E there exists an interval I of belonging to the collection G such that X belongs to I and measure of I is less than epsilon. So we have a collection of intervals and we say that this collection of intervals provides provides E with a Vitali cover if for every epsilon positive and X belonging to E. See, this is something like this. See, you have X belonging to E. What we show is that there is an interval I such that X belongs to I, and also with the property that measure of E is less than epsilon. And this provides a covering for each. I mean, this is true for every epsilon. That means you have all sorts of covers that you can develop. However small a interval you can choose or you require, you can choose. That's what it says. Okay, right. Right. So we will give an example which in a way give some insight into this. So we look at Q. Q containing. Let Rn be an enumeration of Q. So you know that the rationals form a countable collection and therefore it can be enumerated as R1, R2, etc. Okay, very countable collection of numbers R1, R2, etc. Now let AB be an interval. It's a bounded interval that you are talking about. And let me take be an enumeration of rationals. Maybe. Now let us define G. Let G be the collection one by K such that and K equal to so you are looking at intervals of length 2 by K. Okay, by choosing K large enough, you can make it the interval length as small as we please. Okay. Now this is a Vitali is covering for E for the interval okay. Now you can do this on any subset. I mean, now we will be quite interested in working on sets with outer measure finite. So we shall now state the Vitali's theorem. Let E be a subset of R and such that the outer measure of E is finite. So we are working on subsets of R whose outer measure is finite. So we are not assuming that E is measurable. Okay, right? For every subset, the outer measure is well defined. Let G be a Vitali cover. Then given epsilon positive, there exists a finite pairwise disjoint collection IN of intervals in G such that the outer measure of E slash union E slash union n equal to 1 to capital N in is less than. What does this theorem say? It says that if E is a subset of outer measure finite and if G is a Vitali's cover, I mean that's quite easy to construct a Vitali's cover. As you see the example that we have looked at, it is there. So you take this E, whatever be E, you know that there is a countable collection of rationals which form a dense collection, and therefore you see that you can choose intervals of the type Rn minus 1 by k to Rn plus 1 by k, where n runs from 1 to infinity and k runs from 1 to infinity. So you have got surrounding every rational point there is a bounded closed interval of this type, and by choosing k you can make it as small as you want. Okay, and by the virtue of the density theorem, you see that this is going to this whole collection would give you a Vitali's cover. Okay, and therefore what the theorem says is that you can select finitely many such intervals such that the complement of this finite collection in E has outer measure less than epsilon. That means nearly you can approximate the set E as a finite collection of intervals. Okay, and this is a approximation when you consider in terms of the outer measure. Okay, so this is a interesting result. Now we will try to compare this with, there is an analogous result for compact subsets of R. What does it say? It says that every open cover has a finite subcover. Okay, you take a compact set, then this is what you have. Okay, right. Therefore, let us now so we will make some assumptions with which we work. Remark: without loss of generality, we assume that all the intervals in G that's one assumption. Okay. Now, one of the remarks that you can make is that this is very important, the theorem that we have stated has very important application in the measure theory. So in fact, it's a structural theorem. Make some remarks. So another remark, some remarks. First remark we make is that it is a structural structural theorem associated with the Lebesgue. So two, note that it is valid for all subsets of R whose outer measure is finite. See, there are non-measurable subsets of R. Okay, but every subset of R has a outer measure. Okay, although there are subsets which are not measurable, for which the measure is not defined. So just note this, that we are talking about with the outer measure finite. So that's the second remark. The third remark is that this result resembles the following topological result, following namely high power theorem. Let us briefly recall what this theorem is all about. Okay, this theorem says that every compact bounded, closed bounded subset of R every can be a finite cover of open sorry, I think I should write it more. With a an open cover, there exists a finite cover. What it says is that if you take any open cover, okay, that may not be finite, of course. Okay. For any choice of an open cover for the compact set has a finite subcover. That means you can extract just finitely many of the sets to give a covering for this. Okay. We can just look at the resemblance of our theorem. Yes. So we prove here that if E is a subset of R with measure of E or M star of E, that is the outer measure of E finite, and has a Vitali cover, by intervals of arbitrarily small lengths. That is, the length is essentially, we are talking about intervals. This is what you call the Lebesgue measure. Then one can almost cover E by a finite subcollection. a finite collection, a finite set collection which is pairwise disjoint. Says that what would be left out after using this finite collection is a set of outer measure 0. Okay, that's what it says. Okay, let us chosen from the now this theorem can be used in our later discussion on the local properties like differentiable. Okay, so we shall get this. So here the sort of things that you have to observe are that it's a finite subcollection, it is pairwise disjoint, and it is chosen from the for any cover of such a collection approximating the given set of finite outer measure. So this is what we try to prove. So let us now work on the proof of this theorem. It's a slightly complicated. Okay. So we will prove this theorem, use induction to prove this theorem. So without loss of generality, we assume that the intervals in G are see the collection that we are going to use are only intervals. Okay, so we assume without loss of generality that they are closed. Okay. Now that's the first step. The second step is, since outer measure of E is finite, from the definition of outer measure, there exists an open set contained in R such that E is U and the measure of U is finite. You know that all open intervals are measured. Okay, therefore m star of U is equal to m of, right? So what it says that you can, how does it come first of all? So you see that how is this m star E defined? M star E is defined as the infimum of all the open intervals, when infimum taken over all open intervals, which cover the set E, or of all open sets which cover E. Okay. Therefore, you see that since it is the infimum of this, there exists such an open set. Right? Now we define, now what we do is, let G naught be defined by the set of all I belonging to G such that I is, that means we consider only those intervals in G which is contained in G naught, sorry, which is contained in U. So such a collection is what is called G naught, and you know that that will provide a Vitali's cover. So then if G is a G naught is also now what one does is we proceed by induction. So for that we begin with any arbitrary interval of G naught. Okay. So let so if this happens to cover E, then you are done. Okay. Then we can choose I2 belonging to G naught such that and if E is already contained in I2, then it is we have chosen a cover. Okay, if not, what you do, we proceed by induction. So we assume that there exists I1, I2, In of G0 such that they are pairwise disjoint disjoint now if E is contained in because what happens is E slash union I1, I2, In, the outer measure is going to be 0. Okay. So if not, there exists X belonging to Ik. Now we have assumed that all these IKs are closed intervals. It's a finite union of closed intervals, therefore it is closed. Okay. Now being the union of closed intervals. Okay. There exists a positive distance between x belonging to E, but x does not belong to okay, and so this is what you have. See, if this is not providing you with a cover for E, then what happens? There exists some x belonging to E which is not inside this, and you know that this is a closed set. Therefore, there is a positive distance from x to this collection, this finite collection. Okay, so let positive these are all elementary topological facts. Okay. Now what one does is, so let us try to work out or draw a figure so that we give you some insight into what is going on. Now this is not an exact picture because E need not be an interval, but probably I would draw E as an interval to make the ideas clear. So let us take this is with a warning that E need not be an interval. And what you have is that this is already covered by a finite collection of, and not necessarily in the same order, can be I2 some IN. And suppose there is an x which does not belong to, this is your E. So this is your E. So suppose there is an x which is not in the union of I1, I2, etc. IN. Okay, but x belongs to E. So this is your E. And then let us work out, at least I will mark out in this figure what it is. It's not a distance to I1 but to the union. So this is equal to eta x. Eta x is a positive distance. Now what we do is we describe how we are going to choose IN plus 1. As follows. Choose IN plus 1 belonging to G naught such that x belongs to IN plus 1. So IN plus 1 takes care of this particular point x belonging to E and measure of IN plus 1 is less than eta x by 2. Half of this is. So it makes sure that it is half of this distance which in turn means the following, that you are taking an in plus 1 with half the distance of eta x. Therefore, you are making sure that in plus 1 is not have an intersection, does not have an intersection with union 1 to n ik. This implies that they do not intersect. Okay? So that is one choice. I mean, one condition that we use to decide on this. But this is not the one alone. Further, we insist on in plus 1 with the additional property that measure of is greater than where where alpha n is defined as supremum of measure of I belong G naught and I intersection ik is empty Okay, what does this mean? So you are having a collection of closed intervals belonging to G naught. Okay. Now, from that so each one has a measure. So it's a bounded collection. Okay. So now you are taking the supremum of the measure of I is an arbitrary interval in this collection, with the property that I intersection ik is empty for k equal to 1. That means those intervals which do not intersect this I1, I2, etc. IN. Okay, right. So in that we take the supremum of the length of these intervals. Essentially, it is the length of these intervals. Okay, that's the measure, and that you designate the supremum of these lengths. You designate by alpha. Okay. Now what have we done? We have chosen in plus 1 greater than alpha n by 2. Okay, right? So you see that you are choosing something from here. Now you see your in plus 1 is chosen with the additional property that this is also true. So you have, what you have is that, see, we want to make sure that it doesn't intersect with ik. So what you have is that measure of ik in plus 1 is certainly less than or equal to alpha n. But we choose such a set for which alpha n by 2 is less than. So this is the condition that we impose. Now this is already there by our choice, but this is something that we insist on. So our choice of in has the two properties. So we have chosen in plus 1 such that it doesn't intersect with I1, I2 union and at the same time in plus 1 this is a specific choice that now what you do is, see, you have chosen in plus 1, so I1, I2 etc. in plus 1, and now if you have x which does not belong to that, still go ahead with the same procedure. Okay, you would be choosing an in plus 2 such that in plus 2 does not intersect with the union k equal to 1 to n plus 1 ik, and the measure of in plus 2 is greater than alpha n plus 1 by 2, where alpha n plus 1 is this, the number that you get out of this, and with I intersection ik empty for k equal to 1 to n plus 1. This is how you make the choice. Okay. Right. Now what we have is this, we make some observations. We have this containing, and we have measure of u is fine. Okay, and you see that the union k equal to 1 to n ik is containing. Okay, right? And you know that these ik's are all disjoint sets. Okay, therefore what you have the following property, namely ik's are disjoint closed intervals G naught we have measure of and what is this? This is actually, that is, since they are all disjoint, what you have is this sigma A equal to 1 to, and this is finite because of the choice of E, because of measure of E star is, or sorry, M star of E is finite. Therefore, this is true. And therefore, what you have is this sigma K equal to 1 to and this is true for the countable collection Ik that you choose by through induction process infinity. We have sigma K equal to 1 infinity. Measure of is less than or equal to measure of finite. They are all disjoint. Okay. So what do you have? This is an infinite series. This infinite series is convergent. What does it say? It says the tail of this series can be made as small as we please. Okay. So this is the consequences are infinity. Not only that, these are all, this is a series of positive terms. So these are all the inferences from this. Now this we are going to make. So so what do we have? Another observation that we make, we have what is the relation alpha n. Look at the choice of alpha n. Now alpha n is less than twice and plus, and this goes to 0. Infinity. So what does it mean? Which implies alpha n goes to 0 as n tends to infinity. So that's the conclusion. Right. Now, I think this in the nutshell gives the mode of construction of the collection of sets ik. So if it's finite, a finite collection works, then it's well and good. If it doesn't, then we are going to this situation. So now what we are going to claim is this. How do we work on this? What we do is, we take the partial sum. The partial sum does not possibly cover, it does not cover this if it is not finitely covered. Okay, then what happens? You have some element in E which is not in the partial sum. Okay, so we make use of that, right? And then show that such excess can be put inside a set of outer measure 0, or that collection would form a set of outer measure 0. So we'll take this. X belong to okay, and then what you can infer is this. This implies X belongs to that's quite easy to see, because you see that this is a superset of, okay, so that comes from there. Now what one does is fix n. Now we want to look at the status of this particular x, okay, the x's that are missing finally in this collection, and see what happens. Fix n belonging, choose n as a fixed natural number. Now since x does not belong to ik, you can choose I belonging to G0 such that I intersection empty for n, and okay. Now you see that measure of IN goes to 0 as n tends to 3. Why it is so? Because you have got this relationship. Okay, alpha n is less than this, and this goes to 0. Okay, right? And this implies what? Alpha n goes to 0 as this we have already observed earlier step. So you can, by choosing n sufficiently large, you can make alpha n as small as we please. That is one of the things that you can. Okay. But you observe that alpha n is less than twice measure of I n plus 1. Because you recall that measure of I n plus 1 is chosen such that this is greater than alpha n by 2. So that choice gives this. There exists some n such that we are talking about an arbitrary interval I, okay, and you see that there is some, see, alpha n can be made by choosing n sufficiently large. You can make this less than measure of I for a choice of I. That is always there because alpha n goes to 0. With that you can choose some n such that alpha n is less than measure of I if we fix I. Now if this is the choice that we make, then what you should have, you recall that this particular, then you should have I intersection I n is not equal to n. Okay, because you look at the choice of that we have made, because in plus 1 is chosen with the restriction that alpha n is less than twice the measure of I. This inequality is there. This is satisfied. Okay, right? So if you are choosing any I, okay, which contains n or which contains the particular x that you have, that is left out in this discussion, then that I should have the property that it is not something of this kind. If this is so, then what happens? By our choice that they are going to, their intersection with I1, I2, etc., In is going to be empty. So that's how in plus 1 will be chosen. But if your I is chosen such that, or in is such that in plus 1 is greater than alpha n by 2. Okay. Sorry. I'm sorry. Alpha n is such that alpha n is greater than, or measure of, this is what we have chosen. If measure of in plus 1 is greater than alpha n by 2. This is what we have chosen. Okay. Therefore, see, if you have a in with this property, then you see that this particular in should have intersection with this union of k equal to 1 to n of ik, right? So this is not equal to, this is non-empty. That's the inference, because otherwise what happens? Our choice of in plus 1 will be therefore the particular I is having this particular property. Okay. So let n naught be the smallest integer for which non-empty. Because we are choosing, this ins in such a way that in has no intersection with in, I1, I2, in minus 1, or in plus 1 has no intersection with I1, I2, etc., in plus 1. They are all picked up from I. Okay. But if your I has a property that I intersection in is not non-empty, okay, then you have this property that there is some n naught for which I intersection in naught is not non-empty. Okay, so let us now make the choice. Let because up to n we have already set everything. Okay, so n naught is certainly greater than, and since I intersection I n naught is non-empty, is non-empty, and x belonging to I, what we have is this as I. So let me take this. This is in. Okay, and this is your I. And suppose x belongs to that. X may be here or maybe here. So also it's somewhere in this. Okay. Now what do you have? You choose n naught to be, or xn naught to be the midpoint of in. Okay. Choose in naught. Okay. Now the distance from x to x n naught is at post measure of I, that is this one. Okay, this is the measure of I. And what is this? This is half the measure of in naught. We are computing from here. So this x could be at the worst scenario, it could be at this extreme end. Therefore, in that case, what is going to be the distance? The distance is going to be this plus this one, or you should have, see, they do not, they have a common point anyway. They are intersecting. Therefore, in naught and I intersect, and therefore you have this, the distance from this point to this point less than the measure of I plus measure of in naught by 2. Now we use these estimates for this. So, but what we have is measure of I plus measure of by 2, because they are all intervals, so I am writing m instead of m star. This is less than by, you see, this is the choice after I do up to n naught. Therefore, this is going to be by our choice. You remember the choice that we have made. Okay. So, we have this inequality. So, this is alpha n naught minus 1 plus measure of you remember the one that connects I, the measure of I with this number alpha n naught. Recall that, the choice that we have earlier. Okay. The choice that we have made is the following, that is alpha n is less than twice m in plus 1. Okay. Or measure of in plus 1 is greater than alpha n by 2. Okay. Therefore, we make this choice. So, replace this n by n naught minus 1. Okay. So, alpha n naught minus 1 comes here, and this is the choice that we have got. Okay. This is greater than this. And this is less than twice measure of by 2 and that's equal to 5 times measure of N naught so this is what you have. So what we have obtained from estimate. So measure of I is less than 5 times that means I has an intersection with IN naught in this case. Okay. Now let J N naught be the closed interval with midpoint x N naught. That means this is the midpoint of that. And then what we are doing is and measure of Jn naught equal to 5 times measure of In. Okay, let us go back to the figure. See, this is the measure of In. When this length is the measure of In. Okay, this length that you have. We are taking xn naught and taking an interval Jn naught with 5 times the measure of In. Okay. So it will see what happens is on this side it will exceed this. This is kept as the midpoint. So what you have is that this is going to exceed this. So the Jn naught is going to be what does it mean? It means that it has captured x in it. Okay, which implies so you are now looking at you have now looked at the status of x which is not in this collection. Okay, so what have we got? See, we are looking at an x that does not, so which does not belong to E slash infinity ik, right? And now you see that x belongs to one to n ik for every n. Okay, now we are looking at the status of this. Then what we prove is that such an x can be packed into Jn and measure of Jn is equal to 5 times measure of n. This is how we have defined the Jns. Now let us work on this. Therefore, what we have is this m star of m star of is less than or equal to sigma n plus 1 to infinity Jn. Okay, and this is less than or equal to 5 times sigma n plus 1 infinity measure of and you know that this tail goes to 0, which goes to 0 as n tends to. Okay, therefore what do we get? Since have m star of E slash union n equal to 1 to infinity in, which is equal to limit n tending to infinity which you know is equal to 0. So this is what we wanted. So that completes the proof here. So the content of the theorem is this, that what it says is the following: if E has finite outer measure, then it can be approximated by the union of a finite number of closed intervals which are disjoint, and as small a length as you want to have. Okay, so this is it's a nice approximation theorem for such sets, all for with m star of E finite. So I think I conclude here. Thank you very much. And that is the Vitali's covering theorem. It is some kind of resemblance with what you call the Heisenberg theorem. Okay, thank you very much.